So hi again, everyone, and welcome back to our third session together. Don't forget, if you've missed either of our past conversations, you can find the videos on our YouTube channel. And if you were unable to be with us last week or to watch the videos, stand by for a very quick recap. These bite-sized corrosion conversations really set out to demystify corrosion and cathodic protection, to try and make the subject a little more accessible to those among us who are bothered by corrosion, but who don't work with it all the time. Neil reminded us that in order for our buried structure to corrode, we need an anodic area and a cathodic area, as well as a metal pathway and, of course, the electrolyte. Now, since it is the anodic area that corrodes, it does make sense that we should try to convert that anode of our system and make it into a cathodic area, which then won't corrode. Now, corrosion people use a lot of acronyms with abandon. And last week, we deconstructed SACP and ICCP, learning that there are two distinctly different approaches as to how we can implement cathodic protection. We can either connect our structure directly to a material which corrodes preferentially or sacrificially. And that is called sacrificial anode cathodic protection, or SACP. The alternative is we can utilize an external power supply and impress a current onto our structure in what we call impressed current cathodic protection, or ICCP. Now today, Neil's going to be looking at SACP in a little more detail. Now, with the red tape out of the way, it's over to Neil.
Thank you, Vanessa. So today's subject is in fact SACP. And we are going to have a look at some of the characteristics of sacrificial anodes and see where they can be used, and also to raise a couple of the challenges which may make some people unsure as to whether it is suitable. So there is a familiar picture, except that notice we're now calling it a bimetallic cathodic protection cell. And there's nothing really surprising about that, because we have an anode that is going to corrode, except that that anode is now no longer on our structure. Our structure is the cathode, which does not corrode. What kind of materials can we use to form these anodes? Well, we saw that aluminium, zinc, and magnesium are three materials which are more active than iron in the galvanic series. We've seen that cathodic protection is something that we should all be familiar with, because we've got a cathodic protection in our house in the form of a geyser. In there is an anode which protects the inside of the geyser from corrosion. We also saw that ships are quite commonly protected with cathodic protection, and the sight of these anodes on the outside of a ship is fairly common. What about pipelines? Here is a photograph of a pipeline with a bitumen coating, and these coatings were very prevalent in large parts of the world, particularly in South Africa, for many years. They've largely been superseded by other coatings which have better electrical resistance characteristics, but there are many thousands of kilometers of bitumen-coated pipe all around the world. Can we use a sacrificial anode cathodic protection in this situation? Well, let's see. The challenge with sacrificial anode cathodic protection is the driving voltage of that anode. Typically, a magnesium anode may have a driving voltage of about 1.5 volts with respect to a copper sulfate reference electrode. The magnesium is the most active of the materials that we use for cathodic protection. If you have looked down here at the bottom of the table, you can see we have magnesium, zinc, and aluminium, all of which are anodic with respect to steel. But that's 1.5 volts. That's not very much, is it? The actual potentials which these materials display are shown in this slide. High purity or high performance magnesium has a potential of about -1.8 volts. Standard magnesium, which is an alloy of magnesium has a lower voltage, but it is a lot easier to produce and therefore a lot less expensive. Aluminium and zinc both have a driving voltage of about minus 1.1 volts. Now that's hardly even enough to light up an LED from a voltage point of view. But it's not all just about the voltage. You will recall that way back in the distant past when you did physics, you learned about a thing called Ohm's law. Well, Ohm's law is one of the electrical principles that we deal with in cathodic protection. It governs the relationship between voltage, current, and resistance. And in order to achieve the current that we need for cathodic protection, we are given the driving voltage by the voltage of the actual alloy. And therefore, the only thing we have left to play with is the resistance. And that resistance represents the resistance of the anode to ground and the resistance of the actual pipeline. The anode itself has resistance which is primarily related to geometry over and above the electrical characteristics of the ground, or in fact even the water that it is immersed in. So the longer an anode, the greater its output current, because the resistance of a long, thin wire anode is considerably less than that of a short anode. And the cross-sectional area of the anode determines how long it's going to last, because that gives us an indication of how much material is actually in the sacrificial anode. Because these anodes are sacrificial, they actually waste away or corrode away whilst they're busy doing their work. The capacity of an anode is determined in this number here called ampere hours per kilogram, which means that if, for example, you had a kilogram of magnesium and you were able to draw 1 amp from that, which would be quite challenging, but in theory you could, then that magnesium would last for 1,100 hours, at the end of which it would be totally consumed. Aluminium has a much higher capacity in terms of ampere hours per kilogram, and zinc has a relatively low capacity. So in order to determine whether or not our system is going to work, we need to make sure that we actually have enough material in the ground to be able to deliver the current we need for the design life. In a pipeline situation, we have the pipeline, which is literally the same as our little laboratory experiment. There's the pipeline, and it is connected via a cable to a sacrificial anode. That's what it looks like in real life. The pipeline is just out of sight in the bottom right-hand side of the photograph, but there is a picture of a magnesium anode with a cable that is attached to it, and that cable will in turn get attached to the pipe. Magnesium then corrodes and prevents the pipeline from corroding. The amount of current that is required is determined not only by the soil conditions, but also by the type of coating that is applied to the pipe. So these days we have very high performance coatings. On the left there, you can see pipes that have been coated with a polyethylene coating system, which has a very, very high electrical resistance. And therefore we need a very small current in order to achieve the levels of cathodic protection that we want. We also have polyurethane coatings, which have a very high electrical resistance. And in this photograph, you can see an installation contractor who is busy coating the joint of 2 pipes that are coated with polyurethane, and they have been laid in a trench. Now, when I first started in the business a few years ago, quite a few years ago, as you can see from the photograph, we used magnesium anodes on pipelines which were primarily coated with bitumen, and we used them in areas of very low soil resistivity. And I remember being told by my then mentor that, no, you've got to install these anodes every 50 meters in order to achieve protection. Well, as time went by and I learned more and more and more about the principles of cathodic protection, I began to realize that there was more to it than just throw an anode in the ground every 50 meters. And we found that the 50-meter spacing was not determined by the actual throwing power, if I can call it that, of a a magnesium or a zinc anode. This illustrates the effect of a cathodic protection system using, in this case, zinc anodes. So if we had a very, very low current density, that's about 30 microamps a square meter, we can space our anodes up to 10 kilometers apart. And the reason why generally we don't have them so far apart is because the current requirement in terms of the life for that anode would mean that these anode banks would have to be very, very large. So it's not the driving voltage that limits the extent that we can protect from a single sacrificial anode. I remember doing a project in the UK 30 odd years ago where we used some sacrificial anodes for temporary protection during construction. And a single anode provided full protection to about 2 kilometers of pipe without any noticeable attenuation. So if these anodes are so effective, why don't we use them more frequently? Well, one of the problems that we have with the sacrificial anodes is that of self-corrosion, which can also be called the efficiency of the anode. Now, magnesium is probably the biggest culprit in this regard. And if you were to put magnesium anodes in the sea, they would dissolve away all by themselves, whether they're connected to something or not. On land, the situation is nowhere near so bad. And we can extend the efficiency of a magnesium anode by surrounding it with a chemical backfill, generally comprising clay and gypsum, in order to prevent the self-corrosion of the anode and thereby maintain the maximum possible efficiency. The other little challenge is that the current density that we draw from the anode, these anodes are what we would like our workforce to be. The more current you push or pull from an anode, the harder it works, the more efficient it is. Here's an example of what I mean. There's one of those magnesium anodes which has corroded away quite significantly, to the extent that this portion of the anode has actually broken off the rest of the anode, which was originally this full length. So self-corrosion is a problem. It is not nearly so much of a problem with zinc and aluminium, which is why we would prefer to use those two materials. But if you think back about those driving voltages, zinc and aluminium have a much lower driving voltage than magnesium. The other challenge that we have is called passivation. Now, passivation is an electrochemical term, which means that the material forms an oxide layer or a film on the surface of the anode, which then acts as an insulator. It goes to sleep. And that prevents further corrosion. Now, we use that in corrosion protection because we have passive metals like stainless steels, for example, where we don't want them to corrode, and we are very happy to have that oxide layer, which is called the passive layer. Again, we can control the extent of passivation of the anodes using chemical backfill in order to maintain the anode active by selecting the correct material for the environment. In other words, we don't go and use the wrong material for the environment. So aluminium anodes, for example, don't work in fresh water. We can modify the composition of the material. So the zinc can either be high purity zinc or an alloy of zinc. The old aluminium alloys that were initially used offshore had mercury in them. These days we don't use those anodes anymore because of the toxic effects of the mercury. And then the actual metallurgical microstructure of the anode is also important in order to ensure that it stays effective. This photograph shows you a test piece of an aluminium anode where the test has been undertaken to ensure that the anode does not passivate at very low surface current densities. In this particular case, this material did not passivate, and you can see that this was actually once very smooth and shiny, it has corroded away and given us an etched surface, showing that the anode has corroded pretty uniformly. We use these sacrificial anodes in various applications. We've already spoken about the use of zinc on ships. Aluminium anodes are particularly used on structures offshore, offshore meaning in the sea. These can be platforms, oil wells, gas wells. They're used for subsea pipelines, and they're extensively used for the protection of jetties, where we have tubular and sheet steel piles going into the sea. As I mentioned earlier, we don't generally use magnesium in the sea because it disappears all by itself without any help from a steel structure. However, there are situations where magnesium anodes have been attached to offshore platforms in order to provide an initial very high current density during the polarization phase of the structure. It has been shown in a lot of research and practical experience that a high initial current helps to ensure that the cathodic protection system works very efficiently over a longer period of time. To give you an idea, this is a photograph of a magnesium anode that was put in seawater for test purposes, and this is only after 30 days. So our offshore structures have vast quantities of aluminium anodes attached to them. You can see, for example, this anode here that I'm pointing to, all the bars that you can see in the photograph, each one of those is 50 to 80 kilograms of aluminium. And the FA platform that was installed off Mossel Bay in the 80s had something like 500 tons of aluminium attached to it in the form of sacrificial anodes. You can see over here that these sacrificial anodes are distributed according to the surface area. And in the area over here, we have pile cluster. There are a whole lot more anodes. And in some cases, these areas are coated in order to reduce the current density and thereby make the cathodic protection more efficient. Offshore pipelines are protected using either half-shell anodes, as you can see in this photograph, or bracelet anodes, as we can see in this photograph. Both of these, the pipeline is weight-coated in order to ensure that it has negative buoyancy and stays put on the floor of the ocean. On the subject of the ocean, we can protect the jetty using cathodic protection. This jetty is being expanded, and this tubular pile that you can see over here is coated against corrosion and will also be receiving cathodic protection. The cathodic protection anodes for that particular structure were mounted on a bracelet, and the internal of the bracelet was coated in order to extend the life of the anodes. Having looked at the marine situation, what about the rest? Fresh water, we generally use either zinc or magnesium. We need to be a bit careful with zinc because it tends to passivate in hard water. So generally zinc will only be used in soft waters. In soils, we use both zinc and magnesium. The challenge with zinc is that we need to reduce the current demand because of that low driving voltage. And in the case of magnesium, we have the problem of a limited life expectancy, typically 12 to 15 years. So there's a photograph of a zinc anode that was applied to the gate, the steel gate of a dam. And this photograph was taken 5 years after installation, and this anode had been immersed for something like 5 years, and you can still see the casting lines on the anode. So this is a very good example of the incorrect application of a material for the environment. Here we have a photograph of the use of sacrificial magnesium anodes. These are magnesium ribbon anodes that have been attached to the valve blade of a big butterfly valve. This valve has been in service in very corrosive water for something like 15 years. And as you can see, the anodes are partially consumed. Sacrificial anodes can also be used to protect the internal surfaces of valve chambers. When I say internal, I'm meaning that the pipe is actually inside a valve chamber, fairly deep concrete chamber, and there are gas pipelines going through it. And the anodes that you can see in the bottom corner over here are there to protect the pipelines in the event that this valve chamber gets flooded. Now, this particular valve chamber was located on the banks of a river, so the chances of it being flooded were quite high. Magnesium anodes in the form of ribbon can also be very effectively used in pipeline rehabilitation situations, such as you can see in this photograph, where a section of a pipeline in a rural area was being refurbished. You can see a pipeline rewrapping team in progress. And as the pipeline was refurbished, so the magnesium ribbon was rolled out in order to provide protection. Now, this was so effective that in an area of the pipeline, and here you can see a photograph of the old pipeline and a replacement pipeline over here on the right-hand side, that the magnesium ribbon was installed to provide temporary protection in an area intended to be about 5 years. And something like 10 years later, when the system was upgraded, the ribbon was found to be still operational. The pipe was well protected. Some pipelines in remote areas have been protected using large banks of sacrificial anodes at distributed locations along the pipeline. This particular photograph is rather interesting because it's one of the few situations where a pipeline has actually been diverted in order to go around the tree. There are other uses for sacrificial anodes. In one of our future talks, we're going to be talking about the effect of AC interference from high voltage AC power lines. And typically, we would use a zinc ribbon electrode in order to protect the pipeline against the effects of AC interference, mitigation of that interference. And so we encourage you to join us in our future talks, where we're going to be covering aspects that we've mentioned today, like coatings and AC interference. And next week, we're going to be talking a bit further about impressed current cathodic protection as opposed to sacrificial anodes.
Thanks, Neil. It's always good to get a refresher on this galvanic or sacrificial anode interaction and some of the locations it can be used. Great. I see we do have a question today, which I'll just read out. I'm working on a reservoir design. Will I need cathodic protection, and can we use SACP? Neil?
Pipelines and reservoirs represent that situation that we mentioned briefly a couple of weeks back, where we have different environments. In other words, the steel embedded in concrete is a passive material. The steel in soil is an active material, and you'll end up with an active passive corrosion cell, and you're likely then to get corrosion of the steel in soil. And this happens very frequently in and around reservoirs. Now, the pipes in and around a reservoir are quite intricate, and the routing is complex. And buried reservoir pipe work is actually a very good candidate for the use of sacrificial anode cathodic protection, because we have these various forms of anodes that are available, and you can customize the protection to suit the pipe layout. It does obviously depend on the conditions of the soil in that area and whether or not the reservoir pipework is connected into a bigger network, which may have other CP installed on it, or it may be connected into, say, an area that has plastic distribution piping, but you still need to protect the steel piping. So in that situation, sacrificial anode is often a preferred choice.
Thanks, Neil. I think it's also worth noting that each reservoir needs to be looked at on its own merits. Sadly, it's not really a one-size-fits-all, but I do hope that we've adequately answered your question. There's been another question. Can one use magnesium anodes for AC interference mitigation?
In theory, yes. The challenge, though, is that the consumption rate of magnesium anodes under the effect of AC interference has not been established. And because of the tendency for magnesium to corrode faster, I would be cautious about using magnesium under AC conditions. That's something for somebody to do in a university research project, actually.
Good point. Another question that's just popped up, are magnesium anodes effective in a stray current environment? That's quite a hot potato question.
We're going to unpack stray currents in a couple of weeks' time. The challenge with any sacrificial anode in stray current environments is the intensity of the stray current. So if we're dealing with relatively minor stray currents, then sacrificial anodes will still work. But if we have high voltages, the voltage from the stray current interference is way, way higher than the driving voltage available from the anode, and will tend to swamp it. So the use of sacrificial anodes in stray current environments is limited.
Now, a last question that has come through might be worth holding over to next week, but I'll put it to you. Can one combine SACP and ICCP in a single system?
Well, the short answer is yes. Often in impressed current situations, you find that there are parts of a pipeline, perhaps in remote areas, where there is a short section of pipeline that the impressed current system does not adequately protect. And in that situation, you can supplement the impressed current in a remote area using sacrificial anodes.
Great, thanks, Neil. And thank you to everyone who's joined us for lunch today. And we will all be back next week as we look at ICCP in a little bit more detail.